All right, guys, we're now moving into 14.2.
There are a lot of extras. How many people are out?
Exactly. We've got a few. 3, because there's one copy for me. So when we look at 14.2, when we look at our launch here, guys, it's okay. Your sick classmates will return, I promise. They've not been fed to the Phoenix Lion yet.
What?
What?
There's a lion?
Nothing. Shh. So, we have to move on. This is recording. There cannot be evidence of the lion.
Maybe we just burn this video.
That's too easy. So when we look at these lines, what do they all have in common? What do they all have different?
They're all straight.
They're all straight.
They're different colors.
They're different colors.
They go through the origin.
They go through the origin point. Somebody said it back there. They're all
Proportional.
They're all proportional. We've already said what it takes to be proportional. We said they're all straight, and we said they're all through the origin. So that made them all proportional. What's the main difference that we see here mathematically? Not just the colors. For now?
They're in different coordinates. Quadrants.
So they pass through different quadrants because they all have unique. What's it called?
Slope.
Slope. The steepness of something. Who here's in ski club? Nobody? Okay. A slope, when you go skiing, is the hill because you're going down a slope. You're going down at an angle. If there were no slopes, skiing would be really lame. So, actually, you could still ski. Snowboarding would be really, really hard. So the big difference here is each of these lines has a unique slope. Now, if you want to be able to reference back to this page, I'm going to quickly tell you what each of these slopes are. My slope, actually the green one, that's really annoying. The green slope here, if we do rise over run, is -4/5. The blue one here is 5/4x. The red one here is 3/5x. And our purple one here is 1/5x.
1, 3, 4, 5.
Where's 2? Good job, Luke.
If we wanted to draw a 2/5, that would have to go to this point here and this point here and go through the origin. So that would be that line if you wanted a 2/5. But I don't. So each of them has a unique slope. Now notice that 3 of them are from the left to right increasing. If from the left to right we are decreasing, that makes my slope negative. So if you see that from the left to right you're decreasing, you automatically know your slope has to be negative. Let's jump to your key concept, because I'm pretty sure I put that first. Yep. So, proportional relationship, 2 things. Straight line passes through the origin. We know that any equation to model it will look like y = mx. If it's not proportional, that's when the plus or minus b comes into play. When you have the y = mx plus b, that means it's not proportional. So, what we call these proportional relationship graphs, fancy schmancy name, linear equation. It's an equation that makes a line. It's a linear equation. Not that fancy schmancy. I was saying that facetiously. Fancy schmancy, linear, not very fancy. Facetious, sarcastic. It's another way to say like sarcasm essentially. Alright, I'm going to go ahead and move on because I do not want to wait for it to draw that. Let's look right in here.
Poor video viewers had to listen to that thing.
I know, I'm sorry. I just turned it off now. I'm trying to figure it out, but I can't get the sound from there to not. It records the sound before it ever gets to any speakers. That's the problem. Is it records it straight from the computer. Talk to me later. I've tried what you're going to suggest. The graph shows distance traveled by a car based off time. Notice you cannot just all of a sudden drive 40 miles. It takes time. So here the independent variable, what you're deciding, is how long do we drive. The dependent variable is how far have we gotten based off how far we drive, or how long we drive. So what is the constant speed of the car? How do we determine speed? Here in America, we normally talk about speed in
Miles per hour.
miles per hour, right? MPH. I've got miles. I've got hours. So all I want to do is compute a miles per hour. So let's choose a point. Here's a point. Looks like a nice point. I've driven 120 miles in 4 hours. What will that division get me?
30 miles per hour.
30. So your speed is 30 miles per hour. Maybe they're on a backcountry highway.
Yeah, where would they go? Where would they go for 120 miles that you can only go 30 miles per hour?
Maybe they're in a snowstorm. You don't know.
Or driving around their neighborhood for 120 miles.
Maybe they're trying to get a kid to fall asleep. People do that.
Yeah.
How far will a car then travel in 2 hours? Well, you can either use what you know about miles per hour, or you can look at your graph. 2 hours, I go up to my graph, find the point, go over to how many miles? 60 miles.
That's not a point. That's a nice point.
How long will it take the car to travel 120 miles? Well, we already answered that one. Zach?
Well, if we multiply so like 60 miles per hour and it's multiplied by 2
Yeah.
and 120 miles. per
Yeah,
hour.
so how many hours?
So you multiply the time.
Yep. What do you get?
4.
4 hours.
Could just look on the graph.
Lots of different ways to get to Florida. And hopefully not at 30 miles an hour. Write an equation in dirt form to model this situation. Notice our distance is our y, our time is our x. This is in y equals mx form. But now, instead of using y equals mx, we're going to write it dirt form. So distance will equal, what's our rate?
Hours.
30. So distance will equal 30 times the time or the hours, whatever you want to put, but I'm going to make it,
H.
crap, if I can line this up again. I'm going to make it d equals 30t just to make it in their dirt form. But below that, also write y equals 30x. Because you are in the y equals mx form. If you are using the dirt formula, you are modeling a proportional relationship. Driving is a great example of the proportional relationship because if you don't drive for any time, you don't go any distance. You have that origin point.
Right.
It's like when you're sitting in the driveway waiting for your parents. You are at the 0, 0 point. The graph shows distance a train. Trains are a very efficient way to get places. Write an equation in dirt form that models this situation. So give it a shot. I'll give you about 30 seconds. Put it in dirt form. I'm sorry. Your problem solving was so hilarious. Right? A couple of them are really good.
I'll never sleep again.
So,
That one's really creepy.
Mr. Hudson, your mom or dad like ever when they start the car and then they have to like check their phone or something like that, or
Yeah.
just like do something in the middle of the driveway and you're waiting to go and then you sit it.
That frustrates me.
It's annoying. We got places to go.
What's
things
the
to see.
rate of this train, Ella?
100.
100 miles per hour. So distance will equal 100 times t.
Oh yeah, darn it.
Questions, comments, concerns?
No.
All you have to do to find that m, here's a trick that you might want to know. When we have a proportional graph, m is y at x equals 0. Or, at x equals 1. My brain got away from itself. So if I follow where my x equals 1 up to the graph and find out what the y value is, that will tell me what the m, that constant of proportionality, what that value is going to be. So a restaurant is running a lunch special where they're giving a third off all prices. Now if you get a third off, what are you actually paying? 2/3. So if I want to write the new price y based off the original price x, my new price will be 2/3 of x. That's it. You just have to think about what am I representing, how do I do it numerically? When you cook a hamburger with a certain percent of fat in it, it's going to get lighter. The fat burns off. So write an equation that models the weight of a cooked hamburger, y, based off the original weight, x, when you know it will lose 1/4 of its weight. Now if it loses 1/4, what's it keep? 3/4. So the new weight, y, will be 3/4 x. Pretty easy, right guys?
Left.
Now my graph doesn't show x equals 1. Now x equals 1 falls somewhere weird. So we need to compare here. And you're going to have questions like this on your homework, so be careful when they pop up. You are comparing this speed, y equals 55x. That's your speed. Your friend made a graph. They said, this is how fast I can type. We need to figure out what your friend's rate is. How can I have the same 3 hands of it? James.
You divide 150
That's the point.
Choose a nice point. James, why did you choose that point where the 150 is?
because it's the first one that matched up with the number.
It's the first one that happens at a intersection. If we look here, this point has the horizontal line, but this point has an intersection. This has a horizontal, but that has an intersection. So this point is my first intersection point. So James said, well, I've got a y value of 150 and an x value of 3. So to do delta y over delta x, I say my m is going to be 150 over 3. What's your rate? 50.
Words per minute.
So your speed, your friend's speed is y equals 50x, where y is the words they can type, x is the minutes they've been typing. Who's faster?
You.
You are. You type 5 more words every minute than your friend
That's
does.
not what I do. I type about 50.
I type about 5 words.
I'm really bad. Really bad.
So if I compare here in the graph, somebody who I haven't talked to yet today, what is the speed of the train in the graph? Olivia. 75 miles an hour. So, which is faster? The car or the train?
The train.
The train. Now, these sort of problems are where it gets really fun. If you've ever heard of or seen the math situations where it's like, You leave Albuquerque in a car traveling at 60 miles an hour. A train leaves Washington at such and such time,
Oh, that's
traveling
like
at
a
this.
SAT
At
question.
what time will the two objects collide? Or at what time will you catch up with the train? Or what? Like those are where those really cool math problems come
SAT
from.
question.
So this is your beginning of understanding all of those relationships.
My brother said there was about like 5 questions that were on his exams that
Yeah.
were about trains and cars
Yeah.
running into each other.
Trains and cars are very